So one of the things you've just brought up was that there are potential alternative models to inflation. And you sort of posit these as being comparison theories. Do they do better than inflation at explaining observations? Are they less fine-tuned? So what kind of models are you thinking about when you mention these?
Right. So first of all, let me not answer this question, but let me answer a question which you didn't ask, namely, given that inflation was predictive, yes, even if it's a toy model, why work on alternatives? And for me, there are two reasons for working on alternatives. One of them is if you want inflation to pass further tests, you have to have alternatives to compare inflation with. And for me, this is indeed one of the reasons that I'm interested in working on alternatives, because when I worked on alternatives, I've discovered things which are very good benchmarks for inflation to probe with future observations. But the second reason is that as long as we don't have a nice embedding of inflation into a consistent theory of elementary particle physics, I think we should keep an eye out on possibilities that a different scenario will emerge naturally. And I'm particularly interested in superstring theory, because superstring theory is a candidate theory for quantizing gravity and unifying all four fundamental forces of nature. So if superstring theory were to really work, it would be quite successful in my opinion. And back in 1988, when I was a young faculty member at Brown, I was every week in Boston talking to a young faculty member at Harvard, Kumon Waffa, the string theorist. And we were trying to ask the question whether inflation would arise naturally from superstring theory. And back at that time, we found that it was not that easy. But we found something that seemed to emerge naturally from string theory, namely a model which is now called string gas cosmology. So string gas cosmology is an alternative to inflation. It is an alternative to the dynamics of the variola universe, and it is also an alternative to giving a theory of structure formation. So that's one alternative, string gas cosmology. There's another alternative which is called the ekpyrotic scenario. Another alternative, the pre-Big Bang scenario. And then there are models which we named matter bounce scenarios. So far I've only given names.
Sure.
And I pause for a moment.
So when you give these models, obviously the names are sort of suggestive in some sense, right? A string gas is a gas of strings and so forth that can lead to expansions and these kinds of things. Right. But when you talk about, for example, a bouncing model, this seems to at least answer some of the questions of inflation in a very natural sense, in that if you extend a cosmology backwards and you say, okay, there was some phase before the Big Bang, or there was some time for these parts of the universe to come into causal contact, to thermalize and so forth, it would seem natural then that one wouldn't have to answer why is the universe the same 180 degrees separated in the sky.
That's right. So the horizon problem, which is a problem that you just mentioned, is a problem of standard Big Bang cosmology, when you assume that the universe was born in a Big Bang and then expanded from then on. However, if the universe is eternal in time, if it's first contracting and then bounces, for example, at a finite radius, or maybe it's a singular bounce, then it's exactly the thermal equilibrium or the vacuum nature that you have at the very beginning that can establish the correlations that you need to explain the isotropy of the microwave background. So the horizon problem is not present in bouncing cosmologies, such as pre-Big Bang, ekpyrotic, and matter bounce.
Yes.
In string gas cosmology, the universe is also eternal in time, and in a similar way, there's no horizon problem. But that's not the only problem that you have to address.
So how would these models address problems like flatness?
So the flatness problem is a problem which distinguishes between inflation and various of the alternative models. So in the ekpyrotic model, the flatness problem is resolved. In the matter bounce and string gas cosmology scenarios, the flatness problem is not resolved as well as it is in inflation. But maybe I should step back and explain the alternatives.
Yes.
So in the matter bounce scenario, you assume that the universe started in a contracting phase, which looks like the mirror image of our present expanding phase. So the universe started with a phase of dark energy domination, then there was a phase of matter domination, then radiation domination, some new physics gives a bounce, and then the universe expands. There's no inflation. What happens is that fluctuations on length scales which exit the Hubble radius during the phase of matter contraction, they acquire the same scale invariance and the same red tilt which inflation predicts. So that's a bouncing, the matter bounce. In the ekpyrotic model, you assume that there's a new form of matter which acts in the contracting phase and which causes the energy density in everything else to decay compared to the energy density in what gives rise to this ekpyrotic contraction. Now in this contracting universe, obviously the energy density in everything expands. It's just that relative to the energy density in this new stuff, the energy density in spatial curvature decreases.
Okay.
So this is how the ekpyrotic scenario solves the flatness problem. In string gas cosmology, that's a different question. And I'll pause.
So I'd like to actually press you a little bit more on the string gas cosmology, because this is obviously something you've developed. And I'd like to ask you then, if one starts with a gas of cosmic strings, if you start with all these interactions, what happens to the cosmic strings?
Right.
Where are they?
Okay, so first of all, string gas cosmology, you start with a gas of superstrings, not cosmic strings. So cosmic strings are objects like vortices in liquid helium, which form in phase transitions in regular quantum matter. Superstrings are completely different. So string gas cosmology comes from the hypothesis that superstring theory is a correct description of nature, and that the elementary constituents of matter and space-time are fundamental strings, which you should visualize as elastic bands. So instead of a gas of point particles, like in standard Big Bang cosmology, we have a gas of fundamental strings. Now, the key observation is the following. If you take a box of fundamental strings and you compress it, then the temperature of this box of strings will hit a limiting value, which is called the Hagedorn temperature. This is very different than what happens if you take a box of point particles where the temperature keeps rising. So you take a box of point particles, you compress it to zero size, the temperature goes to infinity. If you take a box of fundamental strings, you compress it smaller and smaller, the temperature keeps rising to this maximal temperature, and then it starts to decrease. So when the box hits zero size, the temperature is zero. So this was the starting point of string gas cosmology. The realization that if the basic degrees of freedom of matter are strings, the early universe will look completely different. In fact, there's a symmetry between large space and small space.
So in string gas cosmology, you said that the very, very large universe and the very small universe are somehow symmetric. There's a similar behavior between them. What do you mean by this?
Okay, so this is a very deep concept. The equivalence of very small and very large. So the point is that if the basic objects are strings, closed strings, then the universe will look very different at small sizes. And I'm not a string theorist, and so when I talk about strings, I need help. And so therefore help is usually experiment. And you see how I brought with my fundamental string. Okay, now fundamental strings are very different than compared to fundamental point particles. They have oscillatory degrees of freedom. Point particles only have momentum degrees of freedom, center of mass motion. Now there's another degree of freedom which strings have, and this is what I can illustrate that with my hand. Let's imagine that my hand is space. Then strings can wind space. Or, let me make this a little bit clear by taking out my second demo, which is space, a piece of paper. Imagine this two-dimensional space. I take a compact space. Strings can wrap the space. This space is not very robust, and you see the strings will want to make space small. The string windings. String momenta will want to make it large. Okay, so if you have a gas of strings, the energy in the center of mass motion grows as the radius of space decreases. That's an exercise for anyone who's studied quantum mechanics. However, the energy in the winding modes decreases as space becomes small. So if you take a box of strings, you compress it, then below some critical length, the energy will go into the winding modes, and the winding modes will get light. The smaller the size of space is. And from the point of view of the winding modes, the small space will look like a large space. So, a physical observer will see a smallest scale, the string scale. So now you make the connection with cosmology, the Big Bang. There's no Big Bang.
Right.
There's no temperature singularity. There's no size singularity. So the early universe will look very different if matter is described by a gas of strings. So that was the start of string gas cosmology. So then string theory predicts that space is 9-dimensional. String theory is mathematically only consistent in 9 spatial dimensions. So what happens? You start with all 9 dimensions of space wrapped by strings. All 9 dimensions of space remain small, invisible, unless you can remove these winding modes, which you do by having 2 strings intersect and chop themselves off into 2 loops. But since strings are 2-dimensional world sheets, strings evolve in time, this intersection can only happen in 3 + 1 dimensions. So in the string gas cosmology, you get automatically, for free, that out of the 9 dimensions of space, only 3 become large, and the 6 other remain wrapped forever at the string scale. So this was the starting point of string gas cosmology, back 1989, paper by Waffer and myself. And then much later on, we realized that this thermal fluctuations of strings in this early phase can give rise to a scale-invariant spectrum of cosmological perturbations with a slight red tilt, like inflation. But I'm pausing because you're supposed to ask a follow-up question now. Because these calculations we did in 2005, 2006. And that was now not 20 years before the data, but it was substantially after the data. So we post-dicted the results.
Right.
So what are we supposed to do?
Well, predictions for the
predictions. Okay. So 2005, 2006, we actually predicted things that haven't yet been observed, namely spectrum of gravitational radiation. We found also a scale-invariant spectrum of gravitational radiation, but now with a slight blue tilt, whereas inflation gives rise to a slight red tilt. Okay, but let's go away from the specifics. This string gas cosmology is an alternative to inflation. For our picture of the early universe, for giving rise to fluctuations, which makes contact with observations. It is an agreement with current observations. It makes predictions for future observations, with which the scenario can be distinguished from inflation.
So this naturally sort of begs the question of, if we further make observations of a slight blue tilt of gravitational wave spectrum, are you then going to claim that this is evidence not only for string gas cosmology but for string theory in general?
Okay, that's a very good question. I would be a little bit careful. I would now say that, wonderful, we've detected a blue tilt of the gravitational wave spectrum. This was first predicted using a toy model coming from superstring theory. So I would encourage all my string theory friends to say string theory actually has a potential of connecting with observations, and it indeed made a successful prediction. Naturally, this doesn't prove string theory, but it shows that there is a connection between superstring theory and observations, and it shows that superstring theory is not pure mathematics, but it's actually physics. So I'm a very vocal defender of string theory in this sense. But a blue tilt would not prove string theory. You can't say that. In the same way that you cannot say that the present observations prove inflation.
So, as you mentioned this as being sort of a discriminating factor, the red tilt or the blue tilt of the gravitational wave spectrum, are there any other theories that give a blue tilt? Are there any comparison models?
Yes. So some people who like inflation, they basically went back to the toolbox of inflation, and they said that if we abandon the usual energy conditions of matter that are usually central to inflationary model building, then indeed we can come up with a model which has a blue tilt of the gravitational wave spectrum. So technically what you have to do is you have to modify the energy conditions such that you get an early universe which has a phase where the expansion rate increases as time. And the usual matter, which obeys the energy conditions, always has an expansion rate which slowly decreases in time.
So one can achieve this sort of, what I think they usually call it superinflation, right?
Yes.
With increasing Hubble parameter.
Yeah.
I mean, any universe which bounces at a finite radius must have a period in which this happens, correct?
Yes, but in order to get this bounce, you have to violate the energy conditions.
Yeah. Well, if you believe general relativity.
If we believe general relativity.
If you're willing to introduce corrections like Starobinsky does, for example.
That's right. But we take those corrections to the matter side and they look like matter.
Okay.
That violates the energy conditions.
Because, for example, one can do very similar sort of tricks in models like loop quantum gravity, where you take I agree with the gravitational corrections, treat it like matter, and it looks like violation of the matter conditions. Right. So, if one then were to sort of, I'm pushing this blue tilt quite a lot because it seems very interesting, if one were then to see blue tilt, one would claim that this was the first evidence then of some quantum gravity? I mean,
yes.
I suppose what I really want to get at is which would you rather give up, the energy conditions or the quantum or general relativity?
To me it's almost equivalent.
Okay.
Because like if you say that string theory is a fundamental theory, that is basically a modification of both gravity and matter. So to me there's no big difference between the two. But, okay, so if you now were to see a blue tilt in the gravitational wave spectrum. And let me just make a side comment. And the side comment is that 2.5 years ago, there were observations that claimed to see gravitational waves. The BICEP experiment. And if you look at their plot, the data in the paper, you look at spectrum, the spectrum is blue. Except that now we think that it's dust. So again, a slight comment. So I'm very confused why at the BICEP press conference, the results were announced as a proof of inflation. So it's not that I'm very confused about that, but I actually think that it is actually quite a scandal that this was done.
Okay.
Because this is absolutely not the case. If anything, it would disprove standard inflation. We are not, so these data that I'm talking about are not just pie in the sky. So we actually we might have results on the gravitational wave spectrum through B-mode polarization of a cosmic black wave background in a few years, because there are very good experiments which are going to measure B-mode polarization. For example, ACT-Pol, there's an Oxford connection, and the South Pole Telescope. McGill is involved in the South Pole Telescope.
So I want to bring you back a little bit to these model questions of, for example, curvature. So if we lived in a flat universe, the curvature would naturally be zero. And so one can ask how fine-tuned one would say inflation would have to be, or rather one would say an inflation model has to give a result that is somewhat fine-tuned. At what stage do we stop sort of following that quest to understand this better and just say we live in a flat universe?
Yeah, this is a question which I don't have a good answer to. So before we spoke about inflation decreasing the relative amount of energy in curvature. If there's too much initial spatial curvature, the universe may collapse on itself before inflation has time to start.
Right.
So there's somewhat of a tuning of initial conditions in the direction of positive amount of spatial curvature. And but there's a possibility that there's some unknown principle of physics that says that space has to be flat. But this is outside of my area where I have anything constructive to say.
Okay.